All right, well, I'm going to change C, so you can imagine C being edited to say that it tends to make the loop rotate around its axis indefinitely. That's the change I'm going to make. Okay, a lot of stares. Are people ready to vote, or are y'all thinking? Ready? Okay.
Well, not that you changed it.
Definitely. That didn't change your answer?
I want to say it's A and C.
Well, yeah. So I think without changing it, then it could be A or C. That's my thinking anyway. Anybody? I mean, kind of haven't voted yet, but anybody agree with Chris that Jeremy agrees? Jan agrees.
It's always A for all cases. It's only C for if it's not already perpendicular to the direction of the magnetic field. So the case that's drawn on the board is it's already perpendicular to the magnetic field, so it's not going to move. Mm-hmm. But if it was coming from this direction or this direction, then it would cause it to rotate until it came here and it would stop. This is why we have the commutator.
Yeah. The constant current is key too. To get, I mean, just thinking about the lab we did last week, in order to get it to rotate indefinitely, we had to break current each loop.
Yeah.
We had to like stop and then start up again and rely on some inertia. So if it's a constant current through the wire, it's going to make a difference too.
Yeah. Okay, so we've had a lot of people defending A. Does anyone feel strongly about one of the other answers that we haven't covered yet?
How many are going for C?
Anybody vote for C?
Nope. I'm for C.
Just you?
But I'm not strong in my
Okay, well, if you wanted to defend it, you could, but if you don't want to, then...
Defenseless.
Okay. Well, so what Jordan was saying is correct. The picture we have drawn on the board, we see all the forces cancel, and the only instance where you get rotation is where you got a force on one side of the loop that's one direction, and the force on the other side of the loop that's the other direction. Of course, the net force is 0, but that causes a rotation of the loop. And so it's going to rotate until that force is pointing outwards on both loops, and then it wouldn't have any torque anymore, so it would stop, like this picture. So it stops. So if it's worded the way it is now, with C the way it is, yes, in that instance it did rotate, but then it stopped rotating. But that, like Jordan said, that's not going to be true for every instance. There's going to be instances where if this is the orientation of the loop when you turn on the B field, there's no torque to even start, and it wouldn't rotate at all. So C wouldn't be true 100% of the time. And of course, if we change the wording to say rotate indefinitely, then it's never true. So
with that design, it will keep spinning. It's just it won't have a force.
it will only keep spinning if you add a commutator that switches the current direction. That's the only way we can keep it spinning. And so when it says a constant current, that implies that there's no change in the current direction.
How did that work though in our lab when we spun it and it kept going?
Well, in your lab, you didn't even have a commutator. In your lab, you shaved off the coating on your metal wire on one side, and on the other side, you only shaved the coating off of one half of the wire, the top half. And so it's only making electrical contact every 180 degrees. So it gets current 180 degrees. That's what applies the torque to cause it to rotate. But the next 180 degrees, it's not actually getting any current. It's just rotating because of inertia. And then once it rotates around again, now it has current. But if we shaved the coating off of all sides, then your loop would do this. And it would do this indefinitely. And that's not a very useful motor. So that's why we only allow it to have current in one direction, and it only gets current for half of rotation. So that's how your loop actually keeps spinning in the same direction. Okay, so I'm going to edit this so that I think the way it's worded, it could still work. You just it becomes kind of a trick question. I don't know. Okay, so quick review of our concepts that we learned last week. We've kind of reviewed these already, actually, with our discussion, so that's good. I don't know that we really need to spend too much time looking at this slide. Okay, so any final questions about last week's material? All right. All right, so let's talk about the magnetic field due to a current carrying wire. So last week we talked about the force on a current carrying wire. Now we're talking about the force, the magnetic field due to a current carrying wire. So any moving charge creates a magnetic field. We learned that with this equation. So it logically makes sense that if you've got current moving through a wire, those little charges that are moving are creating a magnetic field. So if you look at a small section of wire like this, that's running along this axis, the magnetic field that's created is sort of in a circular orientation around that wire. And we actually have a simplified right-hand rule that can figure out the direction of that magnetic field. You put your thumb in the direction of the current, and you curl your fingers, and the curl of your fingers tells you the direction of the B field. So if the current is to the right, then the B field is going to be making sort of these B field lines that circle around the wire. If you look at a wire that's sort of going into a page of paper like this, that's downward for my current. My fingers curl around, and you'd see the B field making sort of a bullseye pattern around that wire. And closer to the wire, you're going to have a stronger B field, and it's going to drop off like 1 over R. So 1 over R or 1 over R squared? It's just like the E field. Was it E? It was KQ over R squared? I think it was KQ over R squared. I don't know why that's falling out of my head at this moment. But that's the way the B field is going to drop off too, like 1 over R squared. Okay, so let's say we need a method to figure out what the magnetic field is near a current carrying wire. That could be very useful in your electronic devices because you've got a lot of wires running through there, and you can get crosstalk between the wires because of the magnetic fields they produce. Another thing is, I was just running under one of those big power lines at the power line parks, and it was raining, and water molecules, they have sometimes free ions in them. And usually when I run under those power lines, you can hear the power running through them. But when it was raining, I could physically feel my brain like vibrating, which was really creepy. So I don't know if the rain is able to like extend the magnetic field further or something, but that would be something worth knowing. When you've got a lot of current running through power lines, what's the magnetic field near those power lines, and what effect would those magnetic fields have on your body or your electronic devices or your computers if your business is nearby. So this has useful applications. And of course, this is kind of similar to when we found the electric field due to a line of charge. We had to do some ugly integration. So there's that. So we're going to imagine a small section of wire called ds, little bit of s distance, and some point near that wire, a distance r away. To figure out what the B field near that wire is, we have to use a law called the Biot-Savart law. And the Biot-Savart law is really ugly looking. It says that a little bit of B field is equal to this whole function here. We have a new constant here, mu naught. That's the permeability constant. And the permeability constant has a value of 4 pi times 10 to the minus 7th Tesla meters per amp. And as far as writing down the Biot-Savart law, we're not really going to have to do the integration. You're going to observe the integration and then see the result, and you'll get to use the result later. So you can write this down if you want to, but you're not ever going to have to plug anything into this. So we have the permeability constant times the current times the direction of the current, ds, crossed with r vector, the distance away we're looking, over 4 pi times r cubed. And then if you write out the cross product, you'd have I ds r sine theta, and the r would cancel with the r cubed in the bottom, which they've already done, so that's why we have no r on top and we have r squared on bottom. So we're going to take that result, and on the next slide you're going to see how the integration looks in all its ugliness. To kind of make this look more like a math problem, I've straightened out the wire. I've given myself a 0 axis, and the point is on the 0 axis. And let's assume this wire goes to plus and minus infinity, and my little ds is up here, and it makes an angle with that wire of, this angle is theta, so this would be pi minus theta, or 90 minus theta. We're putting it in radians for necessary purposes, because of this, the permeability constant. And if we call this distance from the origin s, and this distance is r, and this distance is x, things that won't change when we integrate, x won't change, but we're going to integrate for every little section of wire, so s is changing as a function of our integration. And then that means this r distance is going to also change. You can rewrite r as the square root of x squared plus s squared. So if we take the Biot-Savart law, in order to, so if you look at it on this slide, you see that it was a little dB and a little ds. If you actually want to find the total B field, you got to integrate that guy. So that's what this looks like when you write it in terms of integration. And I decided to integrate from 0 to infinity and multiply my result by 2, since it's going to be symmetrical above and below the axis. The first thing I needed to do is get everything in terms of one variable that changes as I go up the wire. So right now I've got r that changes and theta that changes, and neither one of them are ds. So I need to get theta and r in terms of s. So r, we can rewrite, we already said, is square root of x squared plus s squared. X is constant, s changes, and that's the integration variable, so that's good. And sine theta we can rewrite as sine of pi minus theta, and that's this little triangle in here. And sine of that angle would be opposite over hypotenuse, so x over r, and then we can replace r with the square root of x squared plus s squared. So now we can replace the sine theta with the term that only has that s variable that's changing. So we make those substitutions in here, and it looks hideous, but the only thing that's changing inside the integration is the s variables. This is something that I personally wouldn't attempt to do on my own. I think that this is one where I've tried to do the integration by hand, and it's not even possible for me. So this is one I had to look up using Wolfram alpha. So we have this ugliness, and we plug that into Wolfram alpha, and it spits out this ugliness. So even the result of integration isn't pretty. Everything out front here, these are the constants that don't change as we integrate. So plugging in my terms of integration, 0 to infinity, then we've got this fraction with infinity on top and the square root of infinity squared, which basically gives you infinity. This little term x squared is like insignificant compared to the infinity term. So basically this term is infinity over infinity, which is 1. And this term is 0 over square root of 0 is 0. So that actually looks gross, but simplifies down quite nicely. And so what you're left with is basically everything that was outside of your integral. So we have mu naught I over 2 pi x. And that's really what the take-home message, right? We don't need to remember the integral. We're not going to have to repeat the integral later. We replace x with r in future dealings, r meaning something different than in this picture. So we'll take that result. And so now, if you're any radial distance away from that, away from a wire, you'll know the B field using this equation. And now we can use R because it doesn't matter if you're up here, over here, down here, or over here, the B field would be the same at that radial distance. So that's why we use R in that equation. So that's what we want to remember. That's the result of the Biot-Savart law.
Question.
Yeah.
So does that tell you the magnitude of the B field, or does it also?
It would just be the
Just the
magnitude.
magnitude, because okay, because I is the current, right? I doesn't really have a direction then.
It has a direction, but it's not a vector. Because you could bend the wire and then your I would change as the wire changes. But your direction for this one, that's a good question, Nolan, because if I said find the magnitude and direction of the B field, this is only going to get you the magnitude. You have to use your right-hand rule to give your direction. So if I said if the current is flowing to the right, what's the direction of the B field? Now you use your simplified right-hand rule and you'd say, be kind of hard to describe it, but it would be curling up over the wire, and in front of the wire it would be pointing down, behind the wire it would be pointing up. You know, so it would probably be easier to draw a picture, actually. Yeah, so that's how you'd figure out the direction, is using your modified right-hand rule. Yeah, Liz?
Could we say, and maybe just if something like this does come up, it would be going like clockwise around the.
Yeah, and it's easier like if you drew the wire coming out of the page like this, then you could draw your B field in a way where you could say that it's clockwise or counterclockwise. Yeah. Yeah, and that's, if it's clear from your picture, then you could even just draw a picture and say this is the direction. I mean, I'm remembering on your homework, whenever it is asked, it's usually a specific area of the picture, so it's not hard to figure out what they're asking to find. So, okay. Oh, Chris?
And if this is for a straight wire, if the wire is then bent, do the magnetic fields that created at each section that interact with each other?
They do, and that's where we're gonna get more equations to deal with that, right? Because we have these loops of wire. That was what we functionally dealt with last week, and so we'll deal with that after we take a break, actually. You know how earlier I said that the B field dropped off like 1 over r squared and it was just like electric fields? Well, I'm lying. This is the equation, right? And it's got r in the denominator, not r squared in the denominator. So it's dropping off like 1 over r, not 1 over r squared. And so if you look at the inverse versus the inverse square functions, they look really similar, just that the inverse square drops off a lot faster. And that's the only difference, is that the B field would drop off at a slower rate than the electric field would. So
is it correct for me to say it's dropping off at a linear rate?
That's not linear.
It's not. I know it's not called linear, but wouldn't that still be a straight line?
It's not a straight line. The inverse plot is not a straight line.
Oh, okay.
Yeah. yeah, you could say it's dropping off in an inverse manner, something like that. Okay, so I'm thinking we can either take a break or we can do this example. Which do you guys feel like you want to do? You guys have momentum and you want to try an example? Okay, so you guys have your packet, and let's see if you can figure out example 28.3 in your groups, and I'll see how you're doing in a few minutes.